Okay, we started? All right, let's get started. Let's see if I can do this in 10 minutes. We need a clock in the back of the room, but maybe people can clue me in. Yeah, every minute, just chirp at me. Okay, I'm here to talk to you about the Nordic Semiconductor radio chips today. Well, actually, just really one of them. I just thought I'd start it out with, they do make a number of different radios, and they do make stuff that's Bluetooth, and they make stuff that's lower frequency than the 2.4 gig radio chip I'm talking about today. And they also make a device which I haven't really looked into. Looks interesting if you're really interested in doing a low-cost product, a single chip solution, which would be a radio chip combined with an 8-bit microcontroller all on one chip. This would be if you were just really trying to make a product that was like a couple of bucks, probably for people who are making things like wireless mice, where two chips knocks them out of the market. They can't swallow that. So what I've got today is the single radio chip, and that it has an internal microcontroller. It handles low-level tasks to alleviate things you'd have to do with your microcontroller if you just were talking to a simple radio device. And really, as I visualize it, the radio aspect of the thing is sitting there doing whatever radio chips do at the lowest level, which would be to ultimately send streams of ones and zeros out over the airwaves. So what this chip does, and I'll pass this around, this is an example of a SparkFun module that uses the radio chip, which is a little QFN package, which is very difficult to hand solder unless you're really good at that sort of thing, and a crystal and a voltage regulator. And then this particular device uses an external antenna. I'll pass that around, and I'll get into what the interface is and also kind of an idea of what kind of software is involved in working with this chip. So I'll just pass that around. So the idea is you've got a microcontroller. In this case is going to be, we'll call it your second chip, or the brain of your device, or whatever, and you're going to be talking to this device. And I kind of wanted to give people an idea what is involved with that process, at least to some extent. You can go read the spec sheet or the data sheet for this device, and probably in a few hours you'll know a lot more than I can bark out here in a few minutes. But anyway, I kind of wanted to give you some idea as to how does this compare to maybe something like an XB, where it's more or less like a UART, or a wireless serial cable type of thing, where you'd be using your microcontroller's UART to talk to the XB, which is very simple, as we all know, more or less. We ultimately can send data from a UART to another device over a serial cable, or through that wireless link that Dick described using the XB, and that process looks like you have a serial cable effectively, with a few other things going on as far as if you're going to have many devices hanging around where you're going to have to address them individually. So anyway, the chip here, one of the functions is it handles assembling the data packets, and this would be the idea of, I want to send data out to some device, and the device will be given a unique address or a number that identifies the device. And with that, I'll couple my data, and then there will be some error check information, the CRC, error check byte or 2 bytes. And in fact, then there's a little bit more information that goes into the packet. There's a preamble that the radio can start listening, and it gets synchronized with the data. And I don't know all the details of that, but that's kind of the idea behind the radio chip, is that you're spared a lot of technical details. That is sort of a specialized area. I'm sure somewhere like at this company there are engineers that's all they do. They specialize in understanding radio, and you don't have to know that much about it at this level. Anyway, what this device does is it's talked to via a SPI bus, which is a clocked serial bus. And the nice thing about that is if you have a microcontroller that's running with a frequency that's not very exact, let's say it's using an internal RC oscillator, it doesn't matter how fast you pump the data to this chip. The chip itself does use a crystal, a 16 megahertz crystal, which through some magic is PLL multiplied to 2.4 gigahertz range. But anyway, as far as talking to the chip, What we're doing is, and I'm not exactly following my slides here. One, we send the data, and a nice thing about the radio chip is it's talking to a like chip at the other end of the link. We'll just consider point to point at this time. The thing is that the device can do some of the things Dick was talking about, where it sends the data, and if you wish, you can have the remote device send an acknowledgement back if it received the data and the checksum worked good, where it feels like there's a high probability of no errors in the data, which, by the way, you can have errors if you have the CRC check. I think some people think that guarantees that you'll have flawless data. It just guarantees you have a high probability that if everything matches up, that it is not have error. And I'm about to have a backup. Oh, this will limit my time. Should say 10 minutes. Okay, onward. Let's. I'm going to advance to the next slide here, where I'm going to talk about, okay, what does it take to hook up one of these radio chips to my microcontroller? And here, what we have is a 5 to 6 pin interface. So a little more complex than having an XB, where you can do it with a receive and a transmit serial data. In this case, we're going to have to dedicate the first 4 wires to handle the basic SPI interface, or clock serial interface. And then also another wire is used, or another signal, for radio enable. And an additional wire that's optional is for interrupt request, whereby the radio chip will tell you a number of different things I'll get into in the next slide, or a few slides down. And let's see, okay, other items are the power supply for the chip is 1.9 volts to 3.6. It has an internal regulator, like the SparkFun module I passed out. That has a 3.3 volt regulator, so that can run on 5 volts. The power requirements are 12 milliamps for receive or transmit. And an example, and I will show you a demo. I have this in a little bag, and I'll explain why. This key fob is a SparkFun key fob, and this is a factory shipped fob from SparkFun, and they provide a sample program that's quite helpful that allows the fob to send messages to another Nordic. In fact, I'll hold it up. Here I have my endpoint here, and this module right here incorporates the radio chip, and this module is an embed microcontroller, which is about a $60 ARM-based controller that has a very nice library. And kind of an interesting thing, and I'll kind of go a little aside on the embed, it's got a very nice online library. The compiler is actually online, where when you log into embed.org, it's what they call, I guess, a cloud computing type of thing, where when you log in, everything you do is online, and when you compile your code, it's done by their server, downloads the code to your device. And anyway, the reason I mentioned that is I just noticed today that they had a nice little library designed to talk to this radio chip, or this Nordic Semiconductor. This is the 24L01 Plus chip. Anyway, somebody had written a nice little library, and I thought to myself, well, rather than talk about how much I suffered writing low-level code for this thing, let me see if I can actually download the code to this embed and describe the pins that I had already hooked up on this proto board. But more or less, you could just hook up the 7 or 8 wires on a breadboard and see if I can get this done in 10 or 15 minutes. Because if I can't, then how am I going to tell people about this? How much time are they going to have to spend? Because I can't tell you how much time with this system, and I'll go into that maybe later. But anyway, I was able to do it in just a short period of time, so I felt really good. And anyway, I have links detailed on that. But if anybody has any experience with Mbed, it was super easy. But likewise for Arduino, and there'll be links at the end of the presentation, and somebody emailed a list yesterday who is involved with doing or selling products for the Arduino. There's a library for the Arduino that makes it very easy to get into using this radio chip. So you don't need to know all the details. But you can dig into the library, and you can dig into the 80 pages of spec sheet for the thing and do a lot of different things. But anyway, I'll demo this at the end of the deal. But so let's move on. And let's see, okay, so here we are. We've talked about power requirements. I should mention that the device can very quickly be put to sleep. So in the case of like the SparkFun fob, their demo application, which has an AVR Tiny24 microcontroller, which has 2K of flash and whatever, half a K of RAM, is coupled to the Nordic chip. And right now, everything is configured and asleep. And it's drawing on the order of a few microamps. I don't know exactly what the Tiny24 draws asleep, but I know this, the radio chip, when it's in shutdown mode, it draws a microamp, which is nothing. So whatever the Tiny24 is using, almost nothing. There's a coin cell powering it, so there's a coin cell in this case that this thing can sit around for a year, no problem, whatever, and be used many, many times. So anyway, let's move on. And I did write this last night, but I have no idea. I have to look at these slides to see what we're talking about. Okay, the device, as we saw, the chip has about 12 or 13 components you need to supply. And when I started in on building a product around this radio, I thought about building my own board. And even with the SparkFun modules, which are a little bit expensive, like about $20, I still went ahead and used the SparkFun module. And part of that is designing 2.4 gigahertz antenna, I don't know, pathways and all the high frequency stuff. I felt uncomfortable. I think it's touchy. And I know when I took the SparkFun fob that has a wire antenna, a PC board trace antenna, and messed with that a little bit, and the thing didn't work. So you know, that's an area of expertise I'm not going to say that I've got. So anyway, so I bought the SparkFun modules, but then the person that posted, and I put a link at the end of this, was talking about like a $5 module that uses the chip. Now that's really great. In fact, if you're going to build a device, I'd probably consider going with one of those low-cost modules instead of trying to lay out your own board. Now if you're going to build a million of them, lay out your own board, and there you can get like the reference design online, and like Nordic Semiconductor's reference design, and you copy what you need to there. You could then build your own circuit board and probably feel like it's going to work when you got through with it. And not to mention too, some of the antenna components are, well, they're inductors, and they have specific tolerances and so forth. So it might be a little bit of an effort trying to get that bill of materials together if you're going to build 50 of these things. So let's see, where are we? I think I've mentioned most of that stuff. Let's talk about the software interface. Okay, so we get our 6 wires hooked up to the thing, and I just thought I'd kind of run down what the parameters are, what's involved in making chip A talk to chip B. And the first thing is there's about 80 channels. The chip's capable of synthesizing 128, but if you want to be internationally acceptable, then you stick to the lower 80, so you go from 2.4 gig to 2.48. And the channels are 1 megahertz apart. The data rate for the chip, there's different speeds. 250K is the slowest, and that's the XB rate. It also will talk at a higher rate, like this fob will talk at 1 and 2 megabits a second. Not that you care for a key fob, but if you have a data link, you might care. The problem with a data link running 1 or 2 megabits a second is your range is decreased. And I should note that on the earlier slide, our transmit power is 1 milliwatt with this device. And there are some amplified device, whatever, add-ons. In fact, the link also for the guy that was selling the low-cost modules had some higher power devices. But the chip itself is really pretty much designed for a 1 milliwatt broadcast power. So, okay, channel. So we're going to have to match our channels on our link to talk from device A to device B. And in more elaborate scenarios, you might have something that switches channels, and they have a thing that I won't go into called Frequency Agility Protocol. You can get on Nordic's site for that. And they have a way of selecting, like you might have 3 channels that you find that you're going to try to use in your link, and if you transmit and don't get a response back, you switch to channel B and you transmit, and the receiver all the while is quickly rotating through its 3 channels looking for a broadcast. And so that would be as I understand it, that would be the method for handling multi-channel with this frequency agility protocol. Overall, I've stuck with 1 channel, and a product I sell is a single channel, and the FCC approval is done on a fixed frequency. Could get you into trouble in some environments, but for now it seems to work fairly well. Okay, enough on channels and data rates. If we're going to talk back and forth, another thing we'd need to do is establish if we're going to have an acknowledgement. So if I'm talking to Paul, as I learned from Dick, I think Dick's, I'm not going to talk to him because he's not going to acknowledge he's fried. Paul still looks awake. If I'm going to talk to Paul, possibly I may just talk to him and send him commands, or maybe we'll, because it's a noisy room and Paul's not paying attention to me because he's talking to somebody else or whatever, then we might decide we need an acknowledgement. So Paul's going to raise his pen or whatever, or he's going to echo back to me some information that I'm going to know that Paul's listening. So if we establish ahead of time whether we care or not about acknowledgements, we need to do that on both ends of the link. And these are the type things in a simple system you might just decide to fix. Like in the case of the key fob, I can't remember what their software, if it's looking for an acknowledgement. I don't think it is, but I could be wrong on that. But we'll talk about that. So that's one way to go. Okay, we agree. I'm just going to send Paul messages and I'm not going to care. So if I transmit to Paul, I'm not going to even bother switching modes to a receive mode to listen. If I know ahead of time we're not doing that. But if we are, here's what the radio chip will do. If I send Paul a message, it immediately switches over to becoming a receiver and listens. Yeah, and then I just caught response. Okay, and I'm done because I had Dick is feeding me the information. I'm the radio chip, and he has quit feeding the information. I'm through. I can go to sleep, and that's what the chip will do all automatically. It'll send a message, and if we're not, if we are waiting for a response and we get it, then good. I'll set an interrupt flag to let Dick know that the message was, transmitted successfully. Now, what the chip will do, and Dick talked about on the XB, is you can program the number of times that we'll retry a transmission. So if we're doing this acknowledgement thing, we can set the number of retries up to 15 that'll happen before I give up. And there's a retry time, and that's a parameter you set, and that's between 1/4 of a millisecond and 1 millisecond, as I recall, or thereabouts. There's about, I don't know, about 4 or 5 different amounts of delay. Now, as far as the variable delay thing, I don't think that's done by the chip. I think you pick a fixed interval for the retry on this device. So if you want to get into more elaborate schemes, you're going to have to involve your host microcontroller, and it's going to have to do some work. But anyway, the big thing is that this chip is doing a fair number of things. Okay, other items, we're going to have to decide if we're going to do a CRC error check or not. We can include it or not, and there are a few modes where it is required. We're going to have to set a destination address. So Paul is going to know between 3 and 5 bytes that will be used, he'll be looking for when he's receiving a message. So we send a message out. If he has a mismatch in that address field, he ignores it and doesn't do anything with it. And we'll say that Steve is the controller, Paul's the radio, I'm a radio, and Dick's a radio. So all the meanwhile, we're doing a lot of things between Paul and I that these guys don't have to be involved in, and that's kind of the whole point. All Dick has to do, once he has me set up with an address, he can just throw a number of bytes of data, and then I'll send it, and we'll sit here and work it out till it's either we give up, oh, Paul is not listening to me, I've done my 5 retries that I've been programmed to do, then I'll set an interrupt flag over here to Dick to say max retries, and we didn't make it. So now it's up to him to decide what he wants to do about that. Whether he's going to now try again, or maybe that'll come to the point where maybe he'll wait 5 or 10 milliseconds. There's different options. So anyway, but those are the kind of things that are parameters. Oh, I should mention the data packet size. There's a method by which you can have a fixed packet size. Like in the case of the key fob, it's programmed for 4-byte data, and it's fixed at that. And by doing that, really, we've shortened the amount of data we have to send. Because if we say, oh, we want to have variable packets because I want to send maybe 10 bytes this time and 16, we have to throw another byte in there to be a length byte to say how many is being sent. So you can shrink things down and make it a very efficient radio link. If we're not real worried about addresses or a lot of radio interference, we can go with a 3-byte address. we could send very little information on a packet. With the case of the fob, you might only need to send 1 byte representing the 5 buttons on this thing and which ones are pressed. So you can make a very compact, low overhead link, and unlike the XB is going to be a little, even though their Series 1 is fairly lean, we can make a leaner system here. Anyway, let's see more, let's see, I think we've got pretty much, we talked about retransmit. Oh, we do have multiple receiver pipes. I should get in just briefly into that. For a simple point-to-point network, we don't need to worry about that, but the technology does allow Paul to receive from a number of different, or receive a number of different addresses. So he can have up to 6 addresses, but they're not totally unique, and that's just a little thing you have to deal with anyway, but so I won't go into elaboration there. But it's designed where the radio can be receiving from multiple sources, kind of like a star type of topology where you'd have multiple transmitters sending data, and yet we could have them with sort of a cluster of addresses where another radio system operating nearby wouldn't be challenged by that, even if it was on the same channel. Which channel is a great way. The 80 channels immediately gets you separated from your neighbor, but the other thing is those addresses discern who's talking. Okay, software interface. I just real quickly here, if you're going to transmit, for example, I just threw this out, kind of what's involved. Well, probably the thing to do is get the library and let it take care of it, and there's a function call that'll satisfy it. But I just kind of, let's say this. So you've got your parameters set up, and usually it's a matching set between the 2 radios as far as they've got to be talking the same speed, the same channel. A lot of things have to be the same for them to cooperate. But so here what we would do on a typical transfer is we transfer the data bytes, and then we just flip the chip enable line, which is one of the wires, to the chip, and it then takes off and does what it needs to do. And then it's just waiting, either polling the chip by reading registers on board the chip or waiting for interrupt line. And that's when you'll get back, in this case of doing the transmission, you'll get an OK, it's great, we got or in the case of not looking for a response from Paul, once the data's been transmitted out of the buffer, we'll get a response that it's OK, even though Paul may not be there to listen for it. But anyway, so there's a few different types of things. Oh, and then the max retries, like we talked about. That's a third case for interrupt on transmit. Anyway, that kind of gives you some rough idea. Okay, if you're going to write code, yeah, so this is like my approach. Okay, you get the 80-page manual and you read it like 20 times, and eventually you catch all the little details. Then it starts simple, and anyway, let's see this. I've got another slide, but let's see. Okay, yeah, start simple, and the embed library I did talk about. We'll have a link to that. We talked about that. And let's see. Okay, Nordic does have an API. I kind of looked at it. It looked complicated to me, and that got into that frequency agility protocol. I ended up implementing that in a product, but I ended up taking it out to get easier FCC approval because the single channel was going to be easier and cheaper. So anyway, we'll talk about that in a sec. Okay, yeah, recommendations. Okay, number 1, I did this, which is blindly operating this device here, which is the Tiny 24, inside this, programming it with an AVR programmer, and then kind of hoping it would work. And go through endless cycles of, oh, it doesn't work, because these radios, it's like, nothing happens when not everything is perfectly set up. So one little glitch, wrong channel, wrong address, wrong data rate, wrong data size, you're dead. I mean, nothing happens. So unless you have something to monitor the airwaves, which would be a handy thing to have a radio spectrum, whatever, sniffer, that would be helpful. Really what you want to do is you want to get a little further along. Oh, by the way, I did dump variables to EEPROM. That was crazy too, to try to debug the thing. But anyway, if you have something that at least, like in this case I have an embed, and now I haven't played with this library more than a few minutes, But if the guy who wrote the library doesn't have it, the first thing I do is I'd write something to query all the registers on board the radio chip and display them for me. And that'll tell you a lot, because then you do that for this end. And then for this end, yeah, skip developing stuff on the key fob for a while. Just get another smart end with another good microcontroller that has a serial port that you can hook to a terminal so you can debug your radio link. Trying to debug yes?
Sorry, looks like we got another note from next door. Is anybody parked in the 6 spaces in front of the building on Monroe?
We're about done. Okay, here it goes. Cost for the chip, $1.50 or thereabouts, I don't know. Relatively cheap. If you're going to try to make a product and mass produce it, yeah, you'll beat out Digi. Module cost, SparkFun, I've done a lot of stuff like the fob's about 20 to 25 bucks, depending on who you buy. But this linklet will have about $5 and somewhere in there, and maybe less. Paul, maybe $3.50 off eBay for, or $7 for two. Anyway, yeah, which 2 is a good number because you got to talk to somebody. Anyway. So that's it. Yeah, if you make your own reference design, I mentioned they have a reference design. Applications, I ripped this right. This is the one thing I didn't, this is not mine. Which, it's a good amount of text. Games, remote, gizmos, robot control, you name it, little sensors, whatever, you know, things that don't have to cost a lot of money. Let's see, FCC approval, that's the one downside here. You want to make 50 of these things, you might want to just put an XB in it. Because this you'll have to get a intentional radiation generating certification. Unfortunately, I can't tell you that much about it. My product went to a company and they got it taken care of. They did their certification. I provided a little documentation. Now, the one thing that was handy and cut down on the price is what I did with the key. The fob was originally this send and receive acknowledgement link. I took that functionality out and went with a simple receiver on board mine that does not acknowledge or runs in that mode. And so now the simple receiver is not a radiator and doesn't have to be certified as such. So that cut down the price quite a bit by having a simple receiver, and the fob is transmit only, and I just transmit redundant messages. Yes?
Do you have to worry about FCC approval at all if you're not trying to sell it?
No. No, well, yeah, it's I think the only thing there is if somebody had a complaint, these things are super low power, at a milliwatt, you know, it's like not an issue. So, and the other thing is if you're building it to go into another product where, you know, they're like a hobbyist type thing, I think you're safe there. It's just if you're the end seller where you're pumping the product out, that's what can get you noticed. But the nice thing about the device is it's so low power, I think it must be relatively a breeze to get it through the FCC. Stuff. So anyway, oh, and finally we got the links. So I guess this will get made if this gets published or whatever, but certainly just you can search for Nordic or 24LO1. Anyway, that'll get you a lot of information. SparkFun's got, oh, I don't know, half dozen products. I showed you a few of them, and that's about it. Let's see, we are done. Oh, another one I found helpful was there was a tutorial that a guy wrote, and that was helpful in conjunction with the 80-page manual. So anyway, that concludes it. And questions? Yes?
One point is that if you're buying them off eBay or something like that, you want the plus module. Otherwise, it's the NRF24L01 plus.
Right. Yeah,
that's the newest one.
That's the newest one. There's only a subtle difference. In fact, I thought about selling a bunch of key fobs off because my customer just wants every bit of range they can get. The LO1 was it doesn't transmit at the 250 kilobits, the slower rate. And the slower rate gets you the longer distance. I think that's the only difference, unless there's some other. I think that's about it. I think it'll just do the lower data rate. That's about it. Yes.
And what is the range of the lower data rate?
The lower data rate, well, it depends. The key fob is the one I'm most familiar with. And this has kind of a poor antenna. The FCC looked at this and they saw it was covering like 6 megahertz as far as the bandwidth or whatever. So the SparkFun PC board based antenna that's on this board is not probably the best in the world. But anyway, where was I going? Hang on, I lost my, oh, right. Distance, yeah. Anyway, about 20 feet for the fob to a chip antenna based receiver, about 40 to 50 feet line of sight. if you have like one of these antenna PSMA connectors with the whatever you call the coil antenna, the whatever whip antenna, about 40 to 50 feet. But I think, and one thing I haven't tried is whip antenna to whip antenna to give you an idea there. But again, milliwatt, I think you're going to be around 100 feet. So anyway, that's, and 2.4 gig stuff's a little weird. I think it probably has some characteristics as far as short wavelength and potential reflections. And if I sat here and operate this fob, we may see a little bit of weirdness, which I do have a demo here, but there's not a lot to it. That the SparkFun fob, it's configured kind of cute. They send a button press code, and then they send a number of presses since battery change. I thought that was cute. So it doesn't send the battery voltage, which would have been nice, but they were a little limited on pins. And I really thought about modifying the fob to measure an analog voltage of the battery and send that with every key press, which would be slick, because then you know when your battery will start to go. So, any other questions?
It seems like the key difference between this and the XBs is that this has an SPI interface and the XBs have a serial interface. Do you think that's and then the XB seems slower. Are there other key differences?
The SPI is faster.
Yeah, well,
yeah. This is faster.
Well,
because Dick was talking about at the protocol layer, XB was like 10 kilobits per second, Series 1.
Series 2, 50.
Oh, he was talking about
Series 2.
He was talking about the actual. The bit rates are about the same. The error rate is error AIR rate. For example, 250. Well, this will run faster, but a range compromise. So this will run 1 or 2 megabits a second for air data. But then there's the overhead of the packets. This can run a leaner packet, though. I say that. I feel pretty confident that this will run a little bit leaner in packet lengths. The other thing is, I don't know, although I come to think of it, the XB will transmit you can tell it to time out and transmit a packet. So, or you can even tell it with the API to transmit now, sort of thing. Just trying to think of some of the dynamics there. But this is a little more tricky to configure, I'd say. Although, if you have a good set of library code, then it's not such a big deal. But I do like, of course, the XB for the fact that you can do like a 2 or 3 wire setup. And the other thing is, even though the data communication between your host and this device is quicker, it takes you a little more effort to output that SPI data. Well, if you have a dedicated SPI UART, then, or USART or whatever it be, I guess then you don't have much overhead concerns. One of my things is a lot of these, I've done a number of different designs, and I end up doing like a bit bang SPI interface. So I end up just manually pumping the bits out to the device. And then that starts to cost you. And you'd say, wow, if I could use my UART to jam it out there, then I would. But maybe that argument doesn't hold real well, because most things will have an SPI hardware interface. So maybe I'm kind of, babbling. So, anyway. Is that it? Any more questions? Yes?
On this and Zigbee, both, can you shut down the collision detection?
Ooh, that's a good question. Collision detection here really is just a matter of it happens, I want to say. That was the one thing that you can monitor for clear channel, but I think that is done manually. Your microcontroller would be responsible for asking, I think, is there an RSSI? I think there's a way to ask or kind of look to see if you've got clear air. But ultimately, I think what's going to happen with this device is you're going to transmit, and if there is collision, you're going to end up not getting your acknowledgement back because they're not going to get the data. They're not going to get something's going to go awry there in that stream. Anyway, and of course the XB will do longer packets. I thought that was interesting. This will only do 32 bytes. This will buffer the packets with onboard FIFOs. But the other thing is the XB, well, Series 1, I guess, kind of almost looks like this, I guess. But to do something more like the Series 2 mesh network type stuff, now you're talking about a big software project. And that would be much more overhead for a host controller. But go ahead.
These chips have the mesh capability already.
built into it?
To some
with
extent.
with the 6 points that go out.
Oh.
And then each of those could have another set of points that they're supposed to talk to. So you can actually set up a rather large mesh network.
Oh, okay,
for
okay.
this. Where an XP, you can do the same thing, but
I don't think that's correct, because you have to put these chips into, declare their mode as being primary transmitter or primary receiver.
Right.
And if you're
Right.
primary receiver, then you get 6 channels coming to you. If you're a transmitter, you don't.
but you can also, so what they've done is back to back. So you have your receiver
Two
that
chips?
talks to your transmitter. And with
Oh.
the cost of the chip, so the ones that sell it that are made for mesh networks
Oh, they'll do
are
multiple.
chips back to back.
Oh, 2
Okay.
chips with a microcontroller in between them.
Yeah, with an two SPI.
Yeah, 2 SPIs.
And it just moves
Oh,
in between the two.
uh-huh.
And they're only about $7-8 if you
Oh,
buy
really?
them together.
Oh, okay.
Oh,
And so you can do 6 on both sides, if I
Oh.
understand correctly.
like who, do you know any
With the
manufacturer
channel
names?
flipping.
Any
eBay.
product names?
I don't remember exactly.
Okay.
I have a set at home. But
Yeah,
but it flips through the frequencies, and so you set up your 6 frequencies, and your receivers on the other side, they have their frequencies that are set, and so it
okay.
switches in between them.
Okay. Okay. Wow. Okay. Yeah. So that's.
Anyways,
There's
just saying
possibilities.
You can do it.
Yeah, I mean, I found
Cheaper.
like some things that would be limiting, like the receiver pipe didn't have, it had 5 of the bytes were, well, for a couple of the pipes, 5 of the address bytes have to be the same, only 1 unique.
Right.
So I ended up, because my fobs all have a unique ID, well, how do I deal with that and have a receiver that can receive from multiple fobs? I had to end up embedding some of my address information in my data packet. So, but the cool thing is, though, statistically, with my setup, what happens is because of that one unique address, it helps cut down on the amount of overhead as far as receiving a message that turns out we really don't care about it. Let's see if I'm saying that right. In other words, if we embed part of our address within our data, we end up having to take that over into the microcontroller and look at it and reject it there. Whereas if you have if you did have 6 unique pipes with addresses all unique, the radio would end up rejecting those bad addresses, if that makes sense anyway. I know some of this is kind of, at least you hear the words and then maybe it makes more sense, I don't know. I found this to be tedious and difficult, but I'll tell you what helps is stuff that works when you get like this embed thing up and running and make little changes, incremental changes. I guess that's kind of how we do a lot of things. But I think the thing is if you get a little bit like, I felt like I was really, I don't know, like, oh, I can handle this. And then you kind of get slapped around, and I guess that's what happens to us. At some level, eventually, everything comes together and you read enough or whatever, and you start to understand what you need to do. But anyway, I would have been lost without I didn't like the SparkFun software, and I rewrote most of it. I don't know who wrote it, I forget. I don't want to insult anybody, but at least it was there. And so I ended up rewriting a lot of their stuff, and it helped me to understand the chip. But you don't have to do that. And if you have a simple application, it's not that bad. But you start getting these ideas in your head. Oh, I want this, and pretty soon you'll pay in time. I don't know. That's just me talking. I don't know. What do I know? Anyway, more questions? We're done. Yay!